I'll get something that mimics the original s squared minus 4s plus 4. This is 0, that's 0, that's 0.
Everything's fine.
Yeah. And then you get equals 6 over s minus 2. So fourth. Now this, I'm going to divide, but what is that? S minus 2 squared. So if I divide by another couple of those, now something over s to the 6th would relate to what? What would have to be on the top then? 5 factorial. And that would relate to, that would go to what if you inverse Laplace? T? Yeah, I like it. That matches. That bottom one's always one bigger. Again, I'm memorizing this, but you're starting to see how you could if somebody made you. So this would just be, so if I inverse Laplace both sides, let me just do that for entire right. So y of t equals, now how do I clean this up a little bit? Seeing what I need.
Multiply by 1/6.
Multiply, well, no. What is 5 factorial? It's 5 times 4 times 6. Right? So I already got 6. And whenever you get this factorial stuff and you're seeing what you're missing, just write out what you want and then see what you already got. Right? So I need to multiply by 20, so I better divide by 20. All right, so I get 1/20th t to the 5th, and how do I represent this shift? E to the 2t, which kind of makes sense because that's, I would expect that. Right? E to the 2t would create itself. And the answer better be some e to the 2t something or other. Why are there no constants in there?
No, they're all taken care of.
Yeah, we got enough information to determine everything. There shouldn't be any constants left. Right? Now you could still do all this even if I didn't have information like that. You would just put constants wherever you see y of 0, y prime of 0. You would just put C1 and C2 and just carry it through. You can still do it. It's just that this is very often done with IVPs. Okay. Is that, you guys have done something like this a lot through your calculus careers. This has got to be you got to be used to this. This should feel a lot like integral tables and trying to match it up. That's sort of what this is. Helena. Sort of. All right. Okay. So that's that last one. I just didn't put it on the answer key because I didn't want to make another sheet. All right. Anything you want to focus on? Anything you want to... I feel kind of bad that we had to skip, what was it, 6.3? Is that the one we had to skip? As it gets into, we do 6.2 focuses on ordinary points and what to do about them. 6.3 says, can you do anything if you have a singular point? And yes, you can, if it's a certain kind. You'll start to realize, you guys have realized the progression. Oh, you can do this if all these things. Now, what if you don't have this? Then you can do this weird thing. And what if you don't have this? Then you can do this weird thing. They kind of expand it. That's almost like perturbation theory. You have a simple thing, then it's more complicated, so you add more complicated shit to what you're doing. Okay. Anything you guys want to focus on? Did you try the practice test out? Doing the homework?
Would you mind showing us again? I get it, but just kind of walking us through the steps again on where that s minus 2 to the 4th. I get the
oh yeah, okay.
4th comes from the t, and the 2 comes from that. But can you just show us one more example?
So, I don't know how far back you want me to take it. I could do by definitional Laplacian and set up the integral, but If I did integrate, it'd be by parts several times, right? But we know, I think everybody here should be able to accept that this would be, what would this become?
3 over.
Yeah, so it'd be 3 factorial over s to the fourth. Right, is that cool? Which is 6 over s to the fourth. Now, because of the way the Laplacian is defined, and again, remind me, you're going to have to know this. How is the Laplacian defined?
The integral of 0 to infinity. That's good.
All right, I like it. So that's why it makes so much sense that to shift on the s-axis, I introduce an e to the shift t. Because that would directly just change this. So why does e to the something t mean a shift by that much? Because of the way that we set up this transform. A different integral transform would have a different function here. I would cause a shift a different way. But don't sit there and go, why would e make something shift on the s-axis? What shit's that? Well, it goes back to how we define the transform itself. Is that decent? In fact, here's what we really need. I don't know if you guys even noticed this, but we did a transform from the very beginning. What was the Laplacian of 1? If I wanted to shift that by a, would I do e to the at times 1? How do I shift anything? So up here, if I want to shift that by 2, forward 2, would I just plug in there e to the 2t? Like we did, like it is. And then that, because of this, makes that answer become this. It shifts it over 2. All right, let me stop there. Does everybody see some concerned looks? But there shouldn't really be any concerned looks right there. There really shouldn't. That's at the heart of what this piece does.
So you would just multiply by e to the 8t?
Yeah,
Okay.
anything. If I multiply cosine 3t and if I multiply by e to the at, wherever there's normally an s, there would now be an s minus a. So didn't we know this transform from the beginning? Isn't that 1 over s minus a? But isn't that just transforming 1, shifting it over by a? Any minds slightly blown? I mean, so that is a transform we've seen since we started talking about these things. We just didn't call it. So now I can go back and say, look, I just transformed what 1 does. Ooh, right? I like it. So if I see e to the anything t along with some other function, just wherever s would normally be with that Laplacian is now going to be s minus a, replacing it. That's it. Now when you're working backwards, it gets a little more confusing. There's some examples on the practice test. But let's do an example now. Work it backwards. Everybody cool with this? Because this was not on the answer key. What if I had?
That's how we do number 7b on the practice test. Like e to the
7b is a good example, and then 7c is going backwards.
Yeah.
So let's see. If you haven't tried 7c out yet, what was it? S squared 2s and 5. Yeah. Yeah, Jeff. Is that better? You don't like it?
Yeah.
I'm sorry. It's too damn. Well, when you're integrating, you've had to do something like this before. You haven't done it like a lot. So it doesn't stick in your head as much. But this idea of completing the square and all this kind of crap, you did it way back when to see where the vertex was and crap or something. But I look at this part and I pull that over. That's how I always complete the squares. I say, all right, I'm going to work with you, and I'm just going to forget on you for a minute. You suck, because you're a 5, but you look like an S. All right. What do I have to put here so that this is something squared? You guys remember the process, hopefully, right? Half the middle dude squared. Half of 2 is 1 squared is 1. So if I have to add 1 here, I better subtract 1 there. Right? If I'm going to put the bag of sand up there, I better subtract the gold monkey. I always like to do that. And if he didn't balance his equations correctly, boulder came down. I'm not saying a boulder is going to come crush you, but just pretend like they want you. So so this is the 1. I get 1 over s squared plus 2, yeah, there. I get 1 over s plus 1 squared plus 4. Now what does that look like? What is that? What would it be related to s squared plus 4? Because that's a shift now, we can see. Something with an s squared plus 4 on the bottom. What does it look? What is it trying to be?
Sine.
Sine. And what would the sine require up top?
Constant.
Specifically what constant?
Oh, 2.
2. Yeah. Whatever this is, square rooted, right? So of course now I realize I just have to put a 1/2, so I get a 2 up here. So now when I'm doing the Laplacian, the inverse Laplacian of this, you just put a 2 there. Yeah. That'd be 1/2. What would 2 over s squared plus 4 go to? It would just go to what?
Oh, sine.
Sine
2.
2t, right? So what does this one go to? Sine 2t.
E
Put
to
it on.
the
Negative.
E to the, yeah, negative t. The shift is just by 1. Who cares about it? 4 is a part of the form. You see, 4 is part of the form. What's the shift on the s-axis is the thing that's with the s. Now, if it was cosine, it would be a little harder.
There's 2 on top.
Because cosine, if it was, if there had been an s up top, do you see how it would have been harder? Because if this is an s plus 1, then this has to be an s plus 1 also. So you'd have to maybe play with it in that way too. Okay, you guys start to see any s's there are, they better all be shifted by the same amount before you go throwing shifts around. This is going to affect them all equally.
So I'm guessing you won't give us the formulas then?
For what?
For e to the whatever t times sine and cosine of it? Because I saw in the book they gave us...
Oh yeah, they give you straight
Yeah.
transform formulas?
Yeah, there was
Yeah,
a book,
no.
and then we had to play around with that.
You know I had this somewhere. Because it's an idea that you apply to this paper that I already gave you. You see what I'm saying? That I can live with. I can give you this as a baseline, but then this transform is an idea you apply to this baseline. So I don't feel bad at all, and you guys are like, we know that, Jeff. I don't feel bad at all. I'm not giving you the transform sheet too. Yeah.
So just remembering that every s is replaced with the shift.
With the shift, and this represented by e to the at if it's a shift. Whatever direction a, depending on the sign. I like it. Let's see. So like I said, number 5 actually, I think if I remember correctly, number 5, if I remember it correctly, I thought I had a shift at the end. Yeah, number 5 has a shift at the end. Number 6 has a shift at the beginning and the end. Anybody else need a copy of the practice test? All right. Quinn, you got a copy of the practice test, right? No? Ask everybody individually. All right. So, I mean, if I'm you, you know I'm going to have one question where I ask you to do something with this. It's not going to be like 20 by-part steps, no matter what you think of me. I'm not going to do that to you. I don't even like 2 by, I mean, it's like, I know you know by parts. Why would I make you do it 18 times? It doesn't make any sense. 'Cause? Well, I'll find out if you know. What you're doing. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find out if you know. What you're doing. Well, I'll find All right, do you guys want to do, I mean, I got the answers for these, but still. Yep.
Can we go over a quick definition of singular and ordinary point?
Oh, yeah. Oh, yeah. Well, the nice thing is, whatever ordinary is, singular is anything that's not that. You know, like, so what the hell's ordinary then? Anybody remember? And it dealt with analytic. So what did it mean to be analytic at some point? Anybody remember what that meant? I mean, we kind of boil it down to dealing with polynomials, which makes all of the definitions unnecessary to remember. You can kind of make a shortcut idea, but still, it's good to go back to the idea. Anybody remember what it meant to be analytic? That word came up right when we were talking about power series, so it must have something to do with those.
Oh, it's represented by power series?
Yes. So it's the function that we're questioning if it's analytic. For a function to be analytic at a point, it's not the function has to have a power series representation at that point. You can do it, Chef. And so an ordinary point of a DE, well, let's focus on a second degree because that's what we normally see. Would that be true for x naught? For it to be an ordinary point, what's got to be true? I mean, it's basically that. I mean, it's just that idea applied to the functions in a differential equation. Notice this is after dividing by that, so that's why if there's an x squared out here, it actually becomes non-analytic at 0. Is that cool? So Cauchy-Euler, looking back at that, Cauchy-Euler is a very strange little thing, but because it meets such a rigid set of requirements, and because there's requirements involved, the x's filling in the degrees you lose through differentiation, that's why I had a relatively easy way to do it. But if I just start throwing in random x to powers in front of my y double prime and stuff, oh my god. It's not going to necessarily have a nice or even a possible way to do it. Is that cool? I can't remember that's exactly the way they said it, but yeah, I love it. Yeah, and a point that is not an ordinary point is a singular point. Now again, it's unfortunate, but 6.3 did go into fleshing out types of singular points and which ones had easier things to work with. And if you looked at 6.3 at all, you're like, well, that was not easy. It's kind of weird. It is kind of nifty. Well, I'll let go of that. All right, is that decent? So I do like to give you identification problems. I don't like to ask you just straight up definition questions because I hate that shit. Tell me the definition. But I like to say, identify whether this is an ordinary point for this, just like on the first few on the practice test. Did anybody try out, I was going to say specifically, anybody try out any of these? 2b, especially. I mean, there's an example like that in the book that they do y double prime plus cosine x times y, so you know it's got to be very similar to that. You have to do a few of these infinite summation multiplications. And again, When in doubt, you have to go out like at least 4 non-zero terms. But if I remember, I'll be specific on the test to tell you how far to go out. Because I mean, you're like, well, it's an infinite sum times another infinite sum. You got to tell me how far to go. Especially for my perfectionists. Okay.
We do 2B?
Yeah, sure. So if you do enough of the homework, you start to just memorize what y double prime is and all. You don't have to build it every time. You might want to remind yourself, what is it that we put in place? What is the general power series?
So, infinity. Yeah.
So I really want you to realize when we get to the point where we have like sum n equals, we've worked with something and it's n equals 3 to infinity x to the n, cn plus 2 times n minus 1 times n minus 2 plus cn minus 1, blah, blah. All this is cn. It is a coefficient function of n. So this is really kind of deceptive. This seems really easy. Oh, cn. It's just sort of like the Laplacian is the integral f t e to the negative s t blah blah. What's this? Well, it could be the most disgusting thing anyone's ever seen. Squared. I don't know, right? So it's a little deceptive. The same thing here. What could this be? Almost anything. Shit. Just whatever comes out. Just a function of n. And every value of n, it is a constant coefficient. That's all it has to be. Right? Maybe. That's why this is still a power series. It's still in that form. I don't know. What is this? I don't know. I just made that up. All right. So what's the problem here? We got y double prime sine x y equals 0. So what's y double prime? Somebody got that sucker memorized. Of course, if you don't, you can do y prime and y double prime.
Sum n to 2 infinity cn n times n minus 1 x to the n minus 2.
Let's put c in there. Okay, so that's y double prime. Now, whenever you get one of these where the coefficient is analytic, it's the point that you're working with is ordinary, meaning this is got a power series at that point. You're going to break everything down to its parts. You're not going to leave anything in summation notation because you're going to be beyond that possibility. I don't know if you guys really see what I'm saying. Because you're going to break this down into its parts and break this down into its parts so then you can actually do some multiplication. And of course, in real life, you would do as far as you need to be within error tolerance. And that's how it works in real life. And hopefully your error tolerance doesn't take you out 80 places, but oh well. If it does, you've got software probably do all that shit for you. What sign? Maybe I'll see. Depending on what I put on there, I might give you some power series representations of some of these, especially if I give you a problem like this, obviously. Where does it start? And remember, for small x, sine x is approximately, no, that's cosine. Cosine of 0 is 1, so it starts at 1. Cosine starts at sine starts at x. Oh, have you guys never, some of you guys must have taken physics where you say sine theta is approximately theta for very small vibrations and stuff. That's because the power series representation starts with x. So for very small x, these corrections are basically 0 to most humans. If you don't believe me, do sine of 0.0001 in your calculator. Make sure you're in radians. All right. And then it goes, so cosine and sine fill each other in. So the next one is going to be based on x. No, skip. Well, I'm sorry, yes. So you have constant x squared's gone, x cubed is next. So it's going to be minus And again, if you forgot, it's on, or if you never, I never said you had to memorize this, right? So this is back, I think, 6-1. Yep. But it is kind of nice. Yeah, I like 3 factorial plus x to the 5th over 5 factorial, dot, dot, dot. Times, now write a few, that's got to go here. I might as well break it out so I can multiply this, right? Might as well break it out. So what's the first term here? N equals 0. C0. The awesome thing is, this matches with the power of the x, right? So it'll be plus C1 x plus C2. That's plenty. Equals 0. This is where you start to consider about turning your paper this way, which is actually, I did some of these. There you go. Yeah. I think that's okay. I didn't show every step for all the props, so if you need to see them, I could show it to you. Okay. So we're going to multiply this out, and this is the part that you guys have got to get practice at, and it's not difficult. You're just not used to doing it. Period. So here, let's do a few terms of this. So n equals 2, what do you get? N equals 2 times 1, C2, x to the 0. Is that cool? Plus 3 times 2, 6. So this is for n equals 3, right? And you could, if you want to, you could put n equals 2, n equals 3. Cool. So 3 times 2 is 6. C3, x to the first. Notice this is 2 times 1, 3 times 2. Probably going to be 4 times 3, right? So plus 12, C4, x to the second, because that's going to be 2 off. These are 2 off, 3, 1, 4, 2. So, I mean, this is just exactly where the whole idea of looking for patterns will make things quicker for you. And let's just do one more. All right, where am I at? N equal 4, n equal 5. This would be 5 times 4, 20. C5, x cubed. I like it. Now let's focus on this multiplication. So this is basically the first 4 terms of the second derivative of a general power series. That's what it always looks like. Now how the hell do I do this multiplication? Well, I think I showed you the way I multiply like little do big do. I kind of do it a little out of order so I can collect all the like terms. This is how you have to do this one. So let's see. There's a constant, so I can get x. Is there another way to get just something x? No, because there's no 1 here. If there's a 1 here, I could get it a couple different ways maybe, but I can only get it 1. C0 times x. Now how can I make x squared? How many ways is there to make something x squared? 1. X times the x piece. X squared times 1 would work, but oh shit, there's no 1. So if you look at the example they do with a cosine, they can actually get a few more terms early on because cosine has a 1 here. I like it. You guys keep going.
So the next one would be C1x squared then?
Yeah, because x times c1x is the only way you can make an x squared term. And how do I know? There's an infinite number of things, but they're all higher freaking powers. There's no negative power, so that's the only way I can make an x squared term. Okay, just go a couple more out. Let's see. We'll do a couple more. So now it gets a little more interesting, right? What's one way to make x cubed? Yeah, there's what's 1, basically 1. So C0 times negative x cubed over 3 factorial. So I get, one way to do it is negative C0 over 3 factorial. What's the other way to do it? Yeah, x times c2x squared. So I get plus c2 x cubed. And you don't have to do it the same way I just did it. I just want to collect them as I did it. I want to write all this shit out again. And so you can imagine, like x to the 4th, how many ways is there to do it? I don't have to do another term, because x to the 4th, the lowest I can get with that is x to the 5th, so screw that. What can I do to get x to the 4th? X cubed, and x cubed x, right? So let's see, x cubed, that would be c3 x to the 4th. And then x cubed x would be
C1 or minus C1 over 6.
yeah. X to the 4th. Dot, dot, dot. Thank God for dot, dot, dot. Equals
0.
All right, so now we basically equate coefficients. So we can do this without rewriting all this shit. The only constant term I have up here is this guy. And on the other side, it's just 0. So 2c2 has to equal 0. So c2 is 0. Yay! What are my x terms? How many x terms do I got? I got one here, one there. So then what's the next little equation I can write? 6c3 plus c0 equals 0. So that means that c3 is coolness. You guys, what's that? By this point, hopefully you notice you always solve for the higher because you want it to be based on something that came before it. You define C0, you define C1, that's what the guys think. So you always solve for the higher one in terms of the lower one because the lower one is determined. And I still have to determine the next ones, right? And then I got, what's my x squared? I got x squared there. I got x squared there. So I got 12c4 plus c1 equals 0. So c1 equals, oops, you just talked about it, Jeff. I know. I get c1 over 12. c2, c3, c4. I like it. And then one more. Just to show you using earlier things you've discovered.
So
What do I have for x cubed?
20C5.
Yeah, let me do it. This is what I show my Math 90 students. Oh, yeah. Do a different underline. Sure. So then I get 20
C5
C5
minus
minus
9
0 over 6.
plus C2, that's 0. C2 is 0, so then you just start.
Yeah, so 20, and what's C2?
That's 0, and then
Sweet.
C naught over 6 is just.
Yeah, so C5, not a fifth power, Jeff. C5, that's 0. Add that over, divide by 20. So I get C0 over 120.
But why wouldn't we just substitute out C naught over 6? Because we know that negative C naught over 6 is C3, so why wouldn't we just do C3 over 20?
Oh, because you don't want your coefficients based on more than two things. Because it's a second degree. I should have y1 and y2, and y1 should be the C0s and y2 should be the C1s. If I have a C3 here, that means I have to have three things known: C0, C1, and C3. But I do know C3 because C3 is based on C0. Do you see? That's why you want to take everything back to C0 or C1.
Always.
Because then you have the fewest things you have to identify in the beginning. And to be honest, it's not even that. It's being the most honest. You don't want to have a C3 sitting there when it actually is dependent on C0. Why the hell would you pretend like you need a whole other constant? You don't. I like it. So that's maybe a better way to look at it.
Did you solve for like any two constants? Or does that, or because like will there be a problem where?
Well, it's sort of like you could have a problem where you have a sequence and you know this one and this one. And do you understand how that would really suck if you didn't have to do that?
Yeah.
So you don't have to do that. Could I? Of course I could. And then I could work backwards if I don't feel like doing that shit, right? So you always identify the beginning of sequences, and then the iteration makes the further ones based off of those from earlier. Yeah. Do you have to? No. But your guy. Yeah.
So we're getting 2 power series for this. Do we get 4 of each power series? Meaning we have to go 8 times if we're equating everything to C naught and C1.
All right. Let me process what you're asking me. I have a single answer, but it's based on C0 and C1.
Right. So we're going to have 2 different power series.
We have one power series, but I could break it up. It's sort of like, what's the general solution to a differential equation? There's a YC piece, and there's a YP piece maybe, right? And actually, let's just pretend like a homogeneous. There's YC. Well, how many parts could I break that down into? It depends on the order of your DE, right? This is second, so I could break it down into 2. But is it really, isn't this one function? This is one, YC is one function. It's composed of different things, but that's one function. 3 plus t is one function of t, even though it's made of 3 and t. So there is a purpose. Now there are things that we want to identify y1 and y2 separately. We've seen like reduction of order and all this other stuff, depending on knowing what those are, right? I want to be able to identify them, so of course. So I'm not really, there's only a single power series, to be honest, right?
Because it says find the 2 power series solutions. So
Yeah,
Y1.
so that means break it up into y1 and y2.
So at the end, like, will there only be like 2 C naughts and 2 C1s? That's okay? Or
All right, let's see where we are, right? Where are we right now? We got YC equals, let's see, let's start breaking it down. Basically, here's the format I can follow. Right, that's the answer, isn't it? That's Y. So C0 is C0. C1 is C1. C2 is what?
0.
0, sweet. C3,
Negative C naught over 6.
yeah, negative C naught over 6. What's really beautiful is C3 goes with x cubed. So if you got a bunch of zeros in there, you're not going to freak out. If you're on C3, you're on x cubed. Is everybody? Because that's the answer. All this work is just to figure out C0, C1, C2, C3, and what C3 go with? X cubed. So right now, what am I on? I'm on C3, because C2 is 0. What's that a coefficient of? X cubed. So that's what n is right there. So let me see, what else we got? C4, so it'll be minus C1 over 12, x to the 4th. And then C5 plus x to the 5th. And please always put those dots, otherwise I'm worried that you think that it stops.
I guess what I was trying to get at earlier is wouldn't you want to break that up between the C naught?
And of course. So here we go. So y1 is And now I can take all the c's out. And this is really why the book says z0 equals 1 and c1 equals 0. I don't like doing that. It's because, number one, it's unnecessary. Number two, it makes you feel like you can make them whatever you want. It's bullshit. So what is y1? Is all the c0s, right?
1 minus 1 6 x to the third plus 1
And then y2,
X.
x minus x to the fourth over 12. Got that done.
So I guess that was my question earlier. Is do we have to go out 4 terms or?
Oh, I
is
see
that-
what you mean.
That's
I'm
what
with
I
you.
was getting at.
So I would say, I would tell you for this, because, I don't know, I'm pretty sure I signed at least one problem where there was only one c naught. It was in front of x. So y1 equals x, and then y2 is an infinite power series, because we've seen that happen before. Okay, hopefully. Is everybody cool with that problem? So I would break it down to this level if I'm like 3 for this round 3, but in general I'm gonna talk about this one, and then you break out as many actually come out for that one. Yeah.
Why don't you need to put like C0 in front of the equation?
Well, because remember how we did this before? If y1 was x and y2 was e to the 3t, e to the 3x, what was yc? Then I threw the c's in there, right?
C1.
Yeah. I like it. And there were several reasons why we did that, because some of these processes we learned, I didn't need freaking c's in there to muddy it up. So I want to know what's just y1 by itself before you throw constants on it. You see that? Okay. All right, what was that? I was going to do something. Oh, like, here. What's the answer to this DE? How do you solve that real quick? Yeah, you can write the auxiliary equation. What do you got? So what's y1 and y2? Yeah, because what form are the answers in? Yeah, so this will be a 0, that's 1, so it's just a constant. And this, of course, will be e to the negative x. Wouldn't this, if I did it that way, wouldn't this show up as an infinite power series? Right, because doesn't this have a power series representation? And how would this show up? It would just be C0. And that's the only place I'd see it. C0 plus a whole bunch of C1 shit. Because the answer is constant plus this sucker, right? So there should be some problems. I know I tried to assign some problems. Maybe online I wasn't so careful, but where only one C0 showed up and then an infinite number of C1 showed up, it relates to this kind of answer. Okay.
So I guess when that just check the auxiliary.
Oh my God, dudes! If you don't solve these DEs a different, easier way, well, sometimes they're easier. We saw an example that it wasn't easier, but it wasn't that crazy hard. Then you're insane. I mean, that's now. I'm going to give you a problem where the answer is only representable by power series. So there's going to be no way to double check. But in the cases where it's something like, oh my God. I'm going to say use a power series to find the answer, but you're going to go, I could do that some earlier ways. I'm going to do that just so I know what this shit I'm doing. That's coming out right. Okay, I like it, Okay. Let's see. Let me go ahead and give you guys the answers. You might as well do that. So you can start checking that sucker out. Now, especially on the partial fractions parts, I just didn't feel like copying all that shit down, so I just told you what it was. Yeah, 6 was especially fun for partial fractions. Look at those coefficients, right? Yeah. Yeah. I think I showed you that way that I handle Laplacian shifts. I did it on the thing here where I had, for example, number 5, I had to do inverse Laplace of, where'd it go? Why did I leave off the square grill? Of like 1 over s minus 1 cubed, right? And I said that was equal to e to the t. That was the inverse Laplace of 1 over s cubed. You guys shift, get the shift out of the way, focus on this. Okay. I've never seen, I don't think this book did that either, did it? Did I miss it? I've never seen anything officially do that, and I don't care. Because it just makes sense. But oh, yeah.
Can you review that real quick? How they did that shift?
Oh, well, how is this shifted? It's shifted by 1. Yeah. So then it's going to be e to the 1t to get that accomplished. That's cool. We did that one earlier. So that one we did earlier, remind me, it was like 2 over s minus 2 squared plus 4, something like that, right? So the way I would do that is I would do e to the 2t times the inverse Laplace of 2 over s squared plus 4. I like it. And then you can just attack this and you get the same thing we got earlier. Okay, I like it. I understand why some people don't like this because it's basically multiplying intervals in a way, but it's not that. It's the way that the shift idea works. It is a product inside the interval, so it works fine. But I sort of see why some sticklers don't like it. They can just fill in your favorite first. And, you know, like I said before, I think I pretty much almost always go to x to the n just because it's been really drilled in my brain. But to be honest, like we talked about in class, it doesn't really matter as long as you get them all the same. Because then the relationship handles, the form is held. That's all that matters. Do you guys remember this? So you don't have to end up with x to the n times some function of n. It could be x to the n minus 1, it could be x to the n plus 3, wherever you end up. Now, if you don't feel comfortable with that, then always go into x to the n. That'll work too.
Just to clarify, why is 1e singular?
So this one specifically asked if x equals 0 is ordinary or singular. So at x equals 0, can that be represented? Well, at x equals 0, that function is undefined.
Yeah,
Yeah.
certainly.
Yeah. So sort of like that's why they have a power series representation for, I think it's natural log of 1 plus x they gave, right? And there was a problem we had to do minus x. Remember? Why they have 1 plus x? Because natural log of x at 0 is undefined, right? It's asymptotic there. So I could have a power series around 0 for 1 over x plus 1 or 1 over x minus 1, because those are both analytic at 0. But 1 over x, or 1 over 2x in this case, no, it doesn't have a shot. I like it. I can remember at some point they did say where they were talking about if there were polynomial coefficients, how you could look at it more simply than the full definition. I don't remember where that was in here, but because that's what we're normally dealing with at this level is just polynomial coefficients. Here, bottom page 239. Yeah. So notice that's the shortcut. So how can I tell that this is not analytic? Because A2 of 0, how is it not analytic or not? How is x equals 0 not an ordinary point? Because A2 is 0 at x equals 0. That's the shortcut from the definition. If all your coefficients are polynomial before you've divided, that's the shortcut. So they talk about that specifically because that's what we look at a lot when we first look at this stuff. But it's based on a more general definition that you should know if you get into something more disgusting. So what if I had cosine x y double prime minus 3y equals 0?
You divide by cosine. Cosine of 0. So it's ordinary.